Okay, in this video I'm going to begin a series of tutorials on thermodynamics and statistical mechanics. So this of course will therefore be video number 1, and I'm going to discuss now the meaning of temperature and heat. And this will be video 1 of 2 because this one is going to be very vague and general and perhaps very basic, whereas video 2 is going to explain this in terms of entropy. So for that reason this is, I suppose, aimed, it's very general and very basic. So let's first of all talk about temperature. Okay, what is temperature? Okay, so I'm going to say that temperature is the thing that is the same for two objects when they have been in contact for long enough. So it is the same quantity when two objects in contact for long enough. There's supposed to be H there. For long enough. That's a very general description of what temperature is, but you know, it's actually a reasonably good one. So temperature is the same quantity which two objects have when they have been in contact with each other for long enough. Now you should immediately have some questions. You should be saying to yourself, well, surely this is a very vague description or description of temperature, because it's definitely not a definition. So we'll say it's vague. And the reason it's vague is because, well, what does contact mean? What does, for how long? What is the numerical value of temperature? Anything else we can think of? Well, there are other quantities which will also turn out to be the same when two objects have been in contact for what we say is long enough. So we can see that this is a pretty vague description of what temperature is. So how about we look at it, and I'm not going to go into much more detail this time because this is just a general description. However, when two objects are in contact for long enough, it takes the relaxation time. After the relaxation time, they would be at the same temperature. So long enough is the relaxation time. So you put a hot body and a cold body together. After the relaxation time, they have come to the property which they have that is the same would be the temperature. So the temperature is the same for two objects after the relaxation time for those two objects has elapsed. And once the relaxation time has elapsed, we say that the two bodies are in thermal equilibrium. Thermal equilibrium. Alright? So this is one of three types of equilibrium. We have thermal equilibrium, we have mechanical equilibrium, and we also have diffusive equilibrium. So that's pretty much all we need to know about temperature for the moment. Temperature is the property of two objects which is the same when they have been together for they've been in contact for the relaxation time and have therefore come to, as a result, thermal equilibrium. Now while we're at it, so that's temperature. While we're at it, I'd just like to show you that there are three types of equilibrium. So exchanged quantity, A-C-H-E-N-G-E-D. So first of all, if we look at the exchanged quantity and we look at the type of equilibrium. Okay, I said that there are three types of equilibrium. First of all, of course, I said there's thermal equilibrium. And as we'll see in a moment, in order for something to be in thermal equilibrium, the quantity which is exchanged is energy. So there must be an exchange of energy for the two bodies to be in thermal equilibrium. So that tells you that immediately there is a link between temperature and energy. And we'll see later that means there's a link between temperature and heat. Now, when something is in mechanical equilibrium, the property which is the same for the two bodies is their volume, or the exchanged quantity is volume, we'll say. And the third one is diffusive. And when two bodies are in diffusive equilibrium, well, the exchange property is going to be their particles, the number of particles. Okay, so if we think about mechanical equilibrium, this could be this is when expansion can no longer occur. So if you think about a balloon is in mechanical equilibrium when it can be no longer expanded before it bursts. So it's now in mechanical equilibrium. So, and when we're talking about diffusive equilibrium, we're talking about mixing. Alright? So, we're trying to come up with a numerical value for temperature. Well, I said that was one of the things which we were not able to describe. So I'm going to tell you that the scale, or the way we put a numerical value on it, is by using something called the Kelvin scale. The Kelvin scale. Alright? You may have heard of other ones. You may have degrees Celsius, or you would have heard of degrees Fahrenheit. Okay, there are other ones, but they're very arbitrary. The Celsius scale, for example, is, well, what we did was we set the freezing point of water, and we set freezing point, and we set the boiling point of water, and we said that these are the measurable quantities. And then what we did is we set the value 0 for this and 100 for this. That's boiling, not boiling, and that's the Celsius scale. That's very straightforward. And the Fahrenheit scale is something similar, but I'm not going to go into it. But they're quite arbitrary, all right. And the point is, for that reason, we use, scientists use the Kelvin scale. Now, it isn't degrees Kelvin; it's just Kelvin, capital K for Kelvin. So, just to go back, we said temperature is a measure, okay, of temperature is the property of two bodies which they have the same after they've been in contact for long enough. So I'm going to upgrade that temperature, that description, to the following. So temperature is a measure of the tendency of an object to spontaneously give up energy to its surroundings. So when two objects are in thermal equilibrium, when two objects are in thermal contact, when two objects are in thermal contact, the object which spontaneously gives up energy is at a higher temperature. Now let's see, can you see that? Yeah, I think you can. So this is our new description of what temperature is. We say that temperature is a measure of the tendency of an object to spontaneously give up energy to its surroundings. And when two objects are in thermal contact, the object giving up energy spontaneously is said to be at a higher temperature. Alright, so that is going to be our definition of temperature. We've upgraded the definition to this. Okay? So we've related giving up energy to temperature. If the object gives up energy spontaneously, we say that it is at a higher temperature to that object which it is giving the energy to. Now the Kelvin scale is as follows. When we look at compressing gases, all right. So if we look at changing we'll say pressure and temperature of a gas, and we keep the volume constant, we find that the pressure goes to 0 at minus 273. Okay, minus 273 degrees, and that would be Kelvin, excuse me. And if we look at it on a VT diagram, where P is constant, it also goes to 0 at minus 273. Now these are experiments you can do, but the point is that we call the 0 on the Kelvin scale, the 0 on the Kelvin scale is negative 273 degrees Celsius. Okay, so that's what we say, and we say the jump, so 1 Kelvin, it would say the difference between 1 Kelvin and 2 Kelvin is the same as the difference between 1 Celsius and 2 Celsius. However, instead of, their starting points are not the same. 0 on the Kelvin scale is negative 273 degrees Celsius. Alright, now finally, I said I'm going to talk about heat, and this is going to be quite brief. We've said so far that temperature is related to energy, and we said that the body which gives up energy spontaneously is said to be at the higher temperature. So I'm going to give you the definition of heat. Heat is any spontaneous flow of energy from one object to the other object caused by a temperature difference. Okay, so it is a piece of energy. Okay, so that means the unit is the joule. Okay, energy has the units of joule. Now this is very basic. I'm not going to go into any more detail. However, video number 2, I'm going to talk about how we actually get a proper definition of temperature and heat when we look at the entropy. So that is more the hardcore thermodynamics. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on it. Thank you.